I've called this, it's really for the name. I have called this a lecture today, word embeddings, encodings, and their connection to BERT. So it's actually pretty interesting because the story of BERT, although it's a story of transformers, it's better understood in the context of word embeddings. So like the classical word to vec, all right, and encoders, etc. BERT, in a sense, is just a big embedding machine. Okay, so it's a big embedding machine which uses the ideas of the transformer, in particular, the encoder and the attention mechanism that we described last week. And then the second half of it would be, of course, transformers for semantic text similarity, which is the unsupervised after phase 2 or fine tuning, if you want to call it that. And then this is what we covered last week, fine tuning for text classification with your own data. And then here, you know, sequence and token classification. So that's basically where we are. All right, so for this, I'm going to open up so basically, I'm going to switch over to the whiteboard again. And now we can formally start the BERT discussion. So actually, we have word embeddings, we have autoencoders, and then we have BERT. And there's a very strong relationship in the goal. They're all neural networks, obviously. So they're all based on that, but there's a very strong connection there in terms of objectives. So what are word embeddings, first of all? When you guys took 365 or 520, I gave you a problem of clustering some text, right? And you use singular value decomposition, etc. To represent the sentence, you use what technique? What was the name of that technique? To represent any sentence, a sentence or a paragraph as a vector.
Word to vec?
You didn't use word to vec, right?
Oh, bag of words?
Bag of words, very good. Because the story starts with the bag of words. So in the bag of words, we create vectors where the size of the vector is the size of the vocabulary. Do you remember that? Problem is,
sparse.
It's a sparse matrix. You have 50,000 words in the vocabulary. This is really big. It's very sparse. So what that means is tons of zeros, and then maybe a 1 hidden in there, ... 0, 0. Do you see that? This was a problem. But this was the solution for the longest time. Then came word embeddings, which, as you said, was word to vec. So came word embeddings. And in particular, word to vec, but others as well, fast text, etc. You know, many others, right? So came word to vec. So whereas before, the problem had been that we have a sentence and we would encode it with a really large vector, which was very sparse. Right? This is really large, right? So let's say 50,000 or something. So that was a problem. So this is bag of words, bow. And instead, we say, you know what? I'm going to use word to vec. These are called distributed vector representations. What's the advantage of it? The dimensionality of the vector is now limited, let's say to 256 features instead of 50,000. So you can see how that's good. It's also not sparse like this. Instead, all the values here, the 256 features, have values in it. They have values. And also, these are features basically. And each one of these has semantic meaning. So it's no longer sparse and the features have meaning. What the meaning is, you don't know. You don't predefine. You just say, I want 256. You let the algorithm figure, there's obviously in word2vec, there is an algorithm and an objective function, which basically means what is it that you're trying to optimize, right? So there's an optimization involved. Okay, so you optimize the model, and then it's going to learn. So what I want you to understand is the importance, right? From sparse to this, you got more meaning. It's smaller. You also, you do a lot of things, right? That's really important. Now, this assumes that for every text, the words, maybe I didn't say this, that the words are the ones that are being represented like these vectors, right? So this is the word cat for whatever reason, and that's it, right? And word2vec here does the same thing. It's the word cat, but now represented like that. You guys see that? Is this concept making sense so far?
So far.
Okay, so far, great. All right, so that's what we're doing. Well, as it turns out, BERT, let's say, has kind of a similar objective. But it's much more powerful. So what this means is, in the bag of words approach, as I said, you had vocab size, very big, very big, 50,000. Word2vec, you train on a data set. Oops, it should be much smaller. 256. BERT is kind of the same idea. It can also be 256, but but basically the argument is for the specific task. Now BERT, so I should say this. If you apply word2vec to 2.5 terabytes of data, and then you take that to any other problem, like using KNN, etc. This is state of the art, one of these algorithms. If you do the same, apply BERT, the general BERT, phase 1, to that data set, and you get vectors, the performance of BERT compared to word2vec will not be as good. So word2vec is still pretty good compared to BERT. However, if you apply BERT to a specific task, then for that specific task, the embeddings can be better than the generic word2vec embeddings. So for instance, what's going to happen with word2vec is that, let's take the word bank. Obviously, the word bank has multiple meanings, right? It has something to do with rivers, but it's also where money is stored, right? A good analogy is that with word2vec, it kind of just learns one embedding for bank, right? And that's it. With BERT, BERT looks at, whenever it's training, word2vec kind of just looks at the word and the co-occurrence of words. BERT will look at even multiple sense. So, word2vec will look at, let's say, the bank is closed, right? And it kind of just looks at, sort of like that. BERT looks at more. The bank is closed and the robbers broke in. Do you see that? Remember that when you feed the transformer, remember this, we were giving strings of sequences. The cat sleeps and then wakes and then wakes. So it's kind of looking at more context. So for a specific task, the attention mechanism will allow BERT to link these two words, bank and robbers, for instance, in a more strong sense. So whenever it sees this input, the encoding of bank will reflect money. Do you see that? Does that make sense? But if I give it the bank is slippery and eroded, that refers to a river. So when BERT looks at this sentence, it's going to create a vector for bank reflecting rivers. Whereas in the previous example, the bank vector, both of them of 256, let's say, reflects more, banks. So do you guys understand the difference?
Yes.
Yeah. So that's the difference. So I want you to understand that at the end of the day, they're both creating vectors, right? No longer this gigantic vector. Now they create vectors, let's say of 256, but the features are a little bit more fixed in word2vec, whereas in BERT, they're a little bit more, they're better because when you give it inputs, now it knows how to pay attention to the words because it learned that, oh, when I see rubbers and banks, they're talking about bank stuff. When I see, oh, I see bank and slippery and eroded. No, this has got a meaning of river. So every encoding of the word bank through the transformer, it's a little bit different given the context that it's seeing. And so the values here, let's say that feature X2 and feature X50, right? These are the semantic meaning. This one is more about dollars. This one is more about rivers, right? Just to give you an example. So here, for BERT, I think this is good intuition. For BERT, bank would have like a more 1.1, negative 0.1. You see that? Whereas this one, no, actually, did I do this wrong? I did this wrong, correct? If we want this to have a more river meaning, then this needs to be. You guys see that? Whereas here, for this representation of bank for another sentence, it said the bank and the robbers and everything. So obviously the context is more about money, bank stuff. So then this one should be like that. So the encodings change based on the context in a more meaningful way. There's more semantic because BERT has more understanding about what it's seeing, thanks to that attention mechanism and to the extremely large number of layers in the transformer. Whereas word2vec, first of all, it's a very small neural net and it doesn't have attention either. And so although they're both encoding at 256, BERT might have it. Now, keep in mind, though, as I said, for general things, word2vec is probably better. This is for task-specific encodings. So the taking out the vectors, the encodings from BERT don't exactly work really well for every problem, but they're good for that specific task that you trained it for. Any questions so far? No questions? All right, so that's kind of what I wanted to say as far as the this. I'm not seeing any questions. So let's go back then now to the book. So go to the book here. All right, here we are. So you should be seeing the book. All right, so let me make this a little bit bigger. All right, so I'm kind of motivating then embeddings, right? So I have some graphs here. Somewhere in here. I went too far. I'm really lost here. Oh, here we go. So, so semantic vector spaces, right? That's really what we're talking about here. So as you can see, kind of the story of Word2Vec starts with Mikolov et al. 2013, where it's using all these ideas, these vector space ideas, right? And you can see a vector space here. And so before like Word2Vec and all of this came from latent semantic analysis. You can take a read through that one. It's a nice one, you know, but basically the idea of like putting things in a space and then calculating distances here. So this example, I think, should show similar authors, I think, in this space, in this compressed space, I believe. All right, so anyway, if we look at word embeddings and neural nets, that's what I was talking about. Word embeddings look at the co-occurrence of terms in a document, but in a more simplistic way. Mikolov proposed new algorithms to calculate word embeddings, kind of how I described. One of the methods is Word2Vec. The vector space is based on the co-occurrence of the words. You specify a dimension specifically. The architecture just includes an input layer, an output layer, and a hidden layer. So it's not even a deep neural network. The input layer consists of the words in the vocabulary of size V. So you can see it's pretty big. They're one-hot encoded so that you can represent it. So remember, if we have the vector dog, cat, blue, right, for the word cat, we do 0, 1, 0. And this is for a vocabulary of just 3 words. Obviously, if you have 50,000 words, this is of size 50,000. So hopefully this makes sense. So the vocabulary defines the number of neurons in the input layer. These one-hot encoded vectors for the words in the vocabulary are the inputs to the input layer of the neural network. The outputs of the neural network are also the one-hot encoded word vectors, but this time using a softmax function. Similarly to logistic regression, the softmax is used to calculate a probability distribution over the word. So basically, in this case, the probability that word J in the vocabulary co-occurs with other words in the vocabulary itself. So here's a nice little graph. So basically in the training, this is the input. So notice it's a one-hot encoded vector of all the words in the vocabulary. So, we have cat as the word input. So this is a 1, the other ones are 0. We have a neural net of just one dimension. And then we have all the words again as the output. But this time, the idea is that because we have a softmax, let's say we choose for 20 words, we do this on a 20 words that it's similar, 20 words that is dissimilar. And the way to do that is easy. You take a window of the words that are closest to our word in question from the text, and then randomly we pick words that are not close to it, and those become examples of where it's not similar. So then what the algorithm should do is for the words that it's similar, it should give high probabilities, so high values here. And then for the words that it's not similar, it should give low or negative values, right? So you can see, for instance, the cat should have high probabilities for sleeps, for eats, meows, but the cat and the words space, ship, rocket fuel, should, black hole should not be linked. And that's how it learns. Does that concept make sense?
Yes.
Okay, perfect. So that's word embeddings. That's how the algorithm works. Obviously, this is not a transformer, right? But it's based on neural networks. There's no attention mechanism. And it's kind of just looking at what I described, whereas transformers provide more machinery to learn. It's got tons of layers, et cetera, and it's got the attention mechanism. So then that's word to vec, and then we end up with something like this. For every word, we have a vector of size, let's say, 256, where we have the values of it, and they look like this, basically. So for the word Xanax, which is a drug for depression, I think, and now we've got all the values of it, and that's it. And then these values can be plotted in a vector space. Okay, and then we can do inference because the vectors have meaning. If you want to learn more about word to vec, about how it works, I spent a lot of time writing this section 5.4. I explain every little line of code in word to vec, but that's outside of the scope of this semester, but feel free to read through it. Okay, then, so that's actually word embeddings for today. The next topic that I will just kind of quickly go through is autoencoders, just because they're similar too. So that should be section 5.6. Yeah, 5.6, autoencoders. So autoencoders are a type, it's a similar idea. And if you notice, what's key here is that the word encoder. Now you have seen the word encoder before in the transformer, because if you remember, I said that the transformer has an encoder and a decoder, right? So it has an encoder and a decoder. So here's an encoder. So what are autoencoders? Autoencoders are, so although somebody might ask you, have you ever used an autoencoder? And then you would say, no, I've never used one. And then I ask you, have you ever used BERT? And then you say, yes, I have used BERT in my ethics homework. Then I would say, then you know what? You have used an encoder. All right, the only difference is BERT is a very complex encoder versus a plain vanilla encoder that you can build from scratch. Now you can learn everything that you want about simple autoencoders from this example. I'll just kind of quickly go through this. So autoencoders are a type of compression method where a neural network learns how to represent a vector of size m into a vector of size n, where m is much greater than n. So you're compressing it basically. Here, the input and the output vectors in the network are the original sample and the reproduced sample and the hidden layer of the network. Okay, so that's the architecture. So here, the input and output vectors are in the network are the original sample and the reproduced sample, and the hidden layer of the network is the new compressed representation of the input vector. The objective function minimizes the distance or difference between the original input sample and the reproduced output sample. So let's kind of think about this, because this is important for BERT to understand. Oops, there we go. So you should be seeing the whiteboard now. All right, so I'm gonna just finish this topic and then we'll do BERT in the second half, I guess, with the code. We should have time. All right, so an autoencoder, according to that definition, is this. So let's take an example that you guys know really well, MNIST. So the size of MNIST is 784. Size of here is 784. This is the input. This is the output. Do you guys understand that? But here, the hidden layer gives you full control, because you can say, you know what? I want this image to be reduced to size 100. This is the encoding, the neural net. Why does this work? Well, it's similar to word2vec. In word2vec, I just said that you give it words and the words associated with it, and it creates for each word, by the weights are basically the embedding. That's the same here. You know, I take an image that is 784 and I'm going to learn how to represent it as just this hidden layer of 100. Do you see that? I just do that. What's the advantage of this? The advantage of autoencoders is that, let's say that you're learning how to make an image similar to reproduce the image, right? That's the idea. You give it this as input and you should get this image, something very similar, but running through the network. So that means that in the compression, it should get rid of data that it doesn't need, and it should just represent it with less neurons, okay, to get this output. So imagine that all the images are like this of cats. It goes through the neural net and you get same cat. You see that? Now, one key thing about this is, let's say that you train on a data set of cats, but then your autoencoder is built, and now instead of giving it a cat, you just give it a person. What do you think would happen if you run this image through this model? What do you think the output would be intuitively? Just tell me what you guys think. What do you guys think?
It doesn't match.
Hmm?
That it doesn't match.
It's think of what it does. You give it a picture, it gives you a picture. What I'm asking you is, what would this picture look like, do you think? It's not a label like match or no match. It just creates that image. So what do you think that image will look like?
Cat?
Well, if you had given it a cat and then it runs, it gives you a cat. But now you're giving it this person, right? Running through a model that has learned how to reproduce cat images. So what do you think it'll do? Do you think it'll be a cat? Or do you think maybe it could be you made as a cat?
Okay, I see.
You see that? What is the name of this? It's very popular in the media.
Filters?
Nope. Well, filters, I guess, yes, but have you heard
Oh,
of this?
deepfakes, yeah, yeah.
You guys have heard of this term?
Yeah.
You have, right? Deepfakes. Do you see how kind of this would work now with deepfakes? You build a model here, you give it the same image every time. Not, I mean, here and here, right? Obviously, it's going to be a corpus of millions of images. So it learns how to take any image and converts it into a, you filters it into being a cat. But if you gave it like a person, it might catify it, right? It might put whiskers on it or something like that. And so that's where the deep fakes, they're more complicated than this, but they kind of go from here. Does this make sense?
Yeah.
All right, great. So going back then to, so BERT, so I just want to connect this to BERT. BERT kind of works like this. BERT is an encoder too, with many more layers, right? Many more layers. The input and the output, just like with the encoder that we just saw, where it's the same, 764, or 784, is it right? 784, where it's cat and cat, basically the same input, right? In BERT here, same thing. You give it the, but in NLP, the cat eats, the cat eats. Do you see that? Except that the goal of it is that this is, let's say, the label, if you want to think of it that way, and this is the predicted. The cat mask. So you give it the cat mask, and every time it's going to predict the word. Eats, for instance. It compares it to the original input, and which is the output. And so it's going to learn, it's going to train basically to learn the masks. That's why when you apply BERT to this problem, you're able to predict words correctly. Sorry. But if you think about it, it's a similar formulation. The inputs are kind of the same, just like the inputs were kind of the same here, or with a slight variance and difference. Questions about this idea? This was an important thing I wanted to do, which is link these two concepts. No questions, guys? So anyway, so as I was saying, the input and output vectors in the network are the original sample and the reproduced sample. And the hidden layer of the network is the new compressed representation of the input vector. So what that means for our example of BERT is that possibly the last hidden layer of BERT is what? The embedding. Do you guys understand? Very much in the sense of like word to vector, we had the embeddings. It's a similar idea. Not so good for generic tasks, but might be very good for specific tasks. The last hidden layer, because there's going to be, could be 300 layers here, or 1,000, or who knows. But the last one, but actually, this hidden layer may also be good, or one in the middle, right? So there's actually, I've seen papers where they measure the performance of all of these at different stages, but they are basically embeddings of the input of the sentence, basically, as a generic way, if you want to think of it that way. Questions? No questions, really. Okay. So the objective function minimizes the difference distance between the original input sample and the reproduced sample. usually the input and the output vector are the same vector in the autoencoder. However, denoising for images, for instance, in that case, you can think of the input vector X and the output vector Y as the same one, but with a little bit of noise, except that the vector X has noise. Therefore, this is more like Y is similar to X plus random noise, right? So it's got a little bit of noise. So that's kind of like what we're doing, because in BERT, you don't give it the exact same sentence, right? You give it the sentence and then the same sentence, but with one token replaced with a mask that it should learn. So that's the objective of the autoencoder. All right, so that was the other connection I wanted to make to encoders. I was hoping you guys would have more questions. I'm not seeing any questions here. But these are the building blocks that I wanted to discuss before getting into BERT itself, but we'll save that for the latter half of today.